with snow. So I really appreciate for you to be here, for your interest. So I will be telling you about data science, air pollution, and also in the context of climate change. I will be focusing mostly on air pollution because that's where most of the data science challenges are, but all of the data sciences challenges and of course the current political context that we live are of course exactly transportable and applicable to climate change. And then in the Q&A, we can talk more about it. And I'm gonna keep it brief and high level because it's evening and I'm sure everybody's tired and the last thing probably you want is an hour of math or technical stuff. Yes, so I think this is what I'll be telling you about. First of all, I'll tell you the story that is still ongoing about data science approaches to estimate environmental exposures, air pollution and mortality in the largest study to date, which is a study of 480 million person years, and how that has been informing the regulatory standard by the EPA, as well as all of the political criticism around the study. Most importantly, I will talk about what are the data science challenges that are very common every time you're trying to assess the public health impact of environmental exposures, whether it comes from air pollution, whether it comes from air pollution, for example, from wildfires, where it comes from exposure due to droughts or floods or heat wave. So every time we know that under climate change, we're gonna have more often occurrences of extreme weather events and that will lead to higher exposure to contaminants. And what are the most important data science challenges that we need to deal when we want to calculate the public health impact? Calculating the public health impact is fundamental because only through rigorous science calculating the public health impact, we could affect and impact regulation. And so that's what I'm going to tell you more about. The regulations are mostly driven by the total number of lives that are impacted or saved in, if these regulations are implemented. And then I'm going to tell you about the Harvard Data Science Initiative. I'm one of the two co-directors of the Harvard Data Science Initiative, all the things that we're doing, including the launching of a new journal, which is the Harvard Data Science Review. So President Nixon was a data scientist. Yes, he was a data scientist. So in the 1970s, when he's signing the Clean Air Act, and what the Clean Air Act said is we look at the data. If data and the best epidemiological evidence is telling us that the current level of pollution that we breathe is harmful to human health, we need to lower the national ambient air quality standards. We're gonna lower it, and then what we're gonna do? We're gonna look at the data again. And if the data are saying that even at the lower level, the current level, even when they're lower, are still impacting public health, guess what? We're gonna lower again, and then we're gonna look at the data. So there are other things that Nixon didn't do so well, but with the Clean Air Act, he was a data scientist. And guess what? When you're using data and science to inform policy, good things happen. In fact, I think this has been one of the most successful stories about regulatory policy, where by looking routinely at the best possible science, and lowering the national ambient air quality standard. The national ambient air quality standard for PM 2.5 was around 25 microgram per cubic meter, went to 10, 25, went to 20, went to 15, now it's 12, and now it's under consideration of whether or not to be 10. And in the last 20 years, not only fine particulate matter, I'll tell you mostly about fine particulate matter. Fine particulate matters are fine particles that penetrate deep into the lung and cause adverse health effect, are the ones that are caused by burning of fossil fuel, which is the same major sources for greenhouse gases emission. So if you're cleaning up the air, you're also targeting most of the sources of climate change. But not only fine particulate matter, all of the primary pollutants in the airs have been going down quite substantially to the Clean Air Act. this is just an example of levels of particulate matter in PM2.5. Now, the current political climate is, as you might know, not so supportive of environmental regulation. Actually, today on the front page of the New York Times, the first headlines is that the EPA is considering a new rule which said that all of the, unless epidemiological studies are based on data that are publicly available, they cannot inform regulatory policy. And that is a disaster because basically most of the epidemiological studies that try to study health effect of particulate matter are based on patient records. They cannot be made publicly available. So it's really one of the attacks to try to invalidate all of the scientific evidence to stop regulation. So regardless the fact that the levels of PM2.5 and all the pollutants have been going down, there is still this question about, well, are these low enough, right? Are the current level of fine particulate matter still harmful to human health? And again, this is really important in the broader context of climate change because there is a Clean Air Act. The Clean Air Act is a law. And if we demonstrate that the current level of fine particulate matter are still harmful to human health, they have to lower the National Ambient Air Quality Standard. To clean the air from fine particulate matters, there are two most important sources, traffic and power plants, which are the same sources of greenhouse gases emission. So in a certain way, one way to combat climate change, there is a hook that we can use to slow down the emission of greenhouse gases, in addition, of course, to developing fantastic data science tool to understand the public health impact. So we were interested in assessing whether or not exposure to fine particulate matter, even when it's below the current National Ambient Air Quality Standard, is increased mortality risk. If the answer is yes, again, because of our data scientist, President Nixon, they have to lower the standard. And then, but also really important, that's where the machine learning world is going to come in, and a lot of our data science is also to figure out, are some populations, some people more affected than others? Who are the more susceptible? How we're going to act on that? Because one thing is lowering the standard, but even if you lower the standard, guess what? Most of the people that are most vulnerable are the ones that are still going to breathe polluted air. So, talking about data science, I think one of the most important things to do in the context of data science, at least has been my experience, is to build data platforms. And more data you have, better linked it is, more powerful information you're going to have for regulatory policy. So what we have done with my lab for the last many years is to bring together all of the possible existing government database on environmental exposures, on health outcome, and everything that we call confounders, which are all variables that could confound the relationship between environmental exposure and health. So the first bucket, we call it exposures and intervention. And what we mean by that, we took data from the Environmental Protection Agency, all of the possible contaminants, all of the possible air pollutants, methane emission, weather data, emission from power plants, coal mines, fracking sites, traffic data, anything you can possibly imagine. I'm going to talk mostly about air pollution here, because it's the most advanced part of the research, but we are building this data platform, by being very comprehensive. For example, we are adding air pollution exposure from wildfires. We're adding exposure to contaminants from floods. We are adding heat waves exposure. We're adding cold wave exposure, right? And then we link to health outcomes. And so we took all of the claims from Medicare and Medicaid for the last 20 years. And for Medicare, we now have 60 million individuals in the United States that we follow over time. We know the zip code of residence, we know their age, gender, and race, we know when they get hospitalized for what, and we know where they died. And then the last bucket we call confounders, right? What's a confounder? Well, if you say that air pollution kill people, well, if the people that died are also the people that are in lower socioeconomic status, and people in lower socioeconomic status breed more pollution, is the pollution or is the poverty, right? So there are all of these variables that you need to account for. We'll talk more about it. So then you can say that it's really the air pollution that is killing people and not something else that correlate with pollution and also affect health outcomes. So we call it confounders. Now I have a little bit of a joke, but it's not much of a joke. Actually, I took a Marilyn Monroe, I twisted Marilyn Monroe quote. I am Italian and I think the right shoes are really important, but I believe that if you give a girl the right shoes and the right data, then she can conquer the world, right? And to me, right shoes and right data together, you know, you have to have both. I think it's really important. So, but seriously, building in this world of data science, wherever it is data from cell phone, from satellite, from wherever you want, building a research data platform that is, I call it, sustainable, that is scalable, that you can always augment data is probably one of the most important things, because that's the foundation for which then you can apply whatever tool you want. I see that some people are taking pictures. You like the Marilyn quote. So the health data, right? So every year, for the last 20 years, I would buy the new files of people that get Medicare. So in the United States, when people turn 65, they're eligible to enter Medicare. So this is, I call it an open cohort. Anyone that you know, your father, your grandfather, they have, when they turn 65, they are in the Medicare system. And then we can follow them over time. And so this is now we have did actually up to 2017. So this is 60 million enrollees per year followed over time. So this creates a cohort, I'm sorry, this is a typo, of 480 million person years, right? So by person years, I mean the number of observations. So how many times the same person is into the data set. Similar for the Medicaid population. We're also taking people, studying people that are in the Medicaid system. That's also very important because these are Americans that are all ages, not only the elderly, but are the ones that tend to have a lower socioeconomic status. Although these data are more complicated because in the different states, eligibility to Medicaid, it's slightly different. So these are the monitoring stations that measure daily levels of pollution in the United States by the EPA. This is public available data you can download. Now, one thing that you can notice is though, that even though it's like widely well monitored, the pollution is well monitored, there are areas in the United States where it's not, where the Medicaid claims we have for every single zip code in the United States. So first data science challenge was that we wanted to take all possible data available to improve the estimate of the level of pollution that people will breathe, even in areas that were not well monitored. And so one thing that we did, and all of this is publicly available, is, oops, sorry, I wanna get this. So basically we use a machine learning algorithm, actually now we have even updated, so it's an ensemble learning. And how it works. So basically the input data is we take data from satellite. So satellite have a daily measure, a 1 kilometer to 1 kilometer grid called aerosol optical depth, which is an imprecise measure of pollution. But they're complete. It's daily, 1 kilometer grid for the last 20 years. Then we take weather data, then we take all kinds of land use data, traffic data, green, satellite imagery, green space, anything you can imagine. Then we take the data from the pollution monitor and we put all into a machine learning algorithm, and we can get as output an estimate of the daily level of fine particulate matter, a 1 kilometer grid for all the United States, which is that map here. We validate the machine learning algorithm at the monitoring station, and we had a good 90 to 95% accuracy. And so that was great because it'll allow us to have for every single person in the Medicare, wherever their zip code is, their daily level of pollution that they breathe. It's not perfect, there is error, and I'm gonna get back to that, but it's much better than what we use. So this is an amazing thing about data science, machine learning, and algorithm for artificial intelligence, because these are black box, but here is perfect as a black box. I don't care what's getting inside the black box. What I wanna know is I wanna get the best possible estimates of exposure to fine particulate matter that is well cross-validated, right? And so in this case, that worked perfect. I have this quote which said, to understand how quickly we are cooking the planet, we need to have good data. To have good data, we need good satellites. And that's what's nice about technological innovation. We have good satellite, the data from satellite are available, and they are free. So we use it. Yes.
Did you concatenate those data sources, or did you train one model for each data source and then use that as an ensemble?
The second, yes. Which, by the way, this is open and important question. There is a paper and published on this topic, and anything that you think that with this data we can do better than what we've done, you're absolutely welcome to try. So this is just the estimates of the average level of fine particulate matter that we estimate throughout the entire study period. And just to give you a sense that now we were able to have the entire national coverage, right, on the estimates of the pollution level. So we came up with this paper, July 2017, which had a wide range, a pretty large coverage in the press, because we linked this fine particulate matter for 20 years to Medicare claims for 20 years, all the confounders, and we show with the population of 60 million American, air pollution, even a level below the national ambient air quality standard, are killing people. So if you just focus, for example, to the table, if you just look at the first row, we have 60 million people. So there are very few studies that do a study on 60 million people, 22 million deaths. But then we have 28 million, if you look at the second to last column, 28 million people were living in areas with the ambient level of fine particulate matter below the national ambient air quality standard. And that was really important because we have a giant population size to assess whether or not level below the safety standard were still harmful. To human health. Now, one thing that we need to always keep in mind, and I'm going to come back to this about the data science challenges. This is a quote by Zhao Limang, who is a professor of statistics at Harvard and the editor-in-chief of the Harvard Data Science Initiative, Harvard Data Science Review. It's important to always keep in mind that big data doesn't mean that you get necessarily the truth. Actually, with big data, if you have the wrong model, your conclusion is going to be even more wrong. And with big data, if they're imprecise, your conclusion will also be more wrong. So I think I wanted to put that out there because I'm going to go back to all of the data science challenges today. We are dealing with this large data set. So conclusion, very simple. I'm going to skip on all of the statistical analysis, but I'm going to go back a little bit more. But this was a massive data linkage, and we analyzed it in the simplest possible way using what I call the Cox proportional hazard model. And so basic Cox proportional hazard model is a regression model, and estimate the hazard ratio, estimate the percentage increase in mortality risk that is associated with every 10 microgram per cubic meter increase in PM2.5. And then we include all of these potential confounders as a covariate. And then if you just focus on the first column, the main analysis is when we look at the exposure at all level. And so an hazard ratio 1.0773 means a 7.3% increase in mortality for 10 microgram per cubic meter. You can see there are highly statistical significance because of the giant amount of data. But what is important is that the second row said low exposure analysis. That's an analysis where we estimate the mortality risk among the people who were always exposed at a level of fine particulate matter below the standard. And actually the mortality risk is higher. So what this is 13%. So what this is suggesting that the relationship between exposure to particulate matter and mortality is steeper at lower level, and at some point it flattens out. And this has been seen consistently in many studies. We also did an analysis where we didn't use any machine learning. We only did an analysis by looking at everyone which was close to a monitor, and we still have a 6% increase in mortality, just to make sure that our results were not completely driven by estimation of the exposure. We also found a lot of differences across the different groups of the population. So the horizontal line is the national average estimate, for which is 7%, that's 7.3%. Black have a much higher risk of mortality associated with exposure of PM2.5, as well as Asian Hispanic. We found higher effect for male than female, and we found slightly higher effect for people that are also eligible to Medicaid, which are people with lower socioeconomic status. Yes?
So why is it that it seems like minority populations have a higher level of uncertainty?
Well, because there are fewer. There are fewer people, right? So, and so, I mean, you see the Native American, right? There are fewer. So what we did here, this was a super simple analysis, which I'm gonna get back. There are problems with this analysis. We just fed the model only for the Native American, and we did feed the model only for the Black, like, so smaller the population, larger the uncertainty. But the question is, the important question is why? Right? And so is that because really pollution is more harmful for Black, or because people of color have more comorbidity, less access to healthcare? How are we gonna fix that problem, right? So I'm gonna turn, and so basically what I'm doing is I'm telling you the story of this paper, where this paper was a massive data intensive analysis, where the statistical analysis were the most straightforward as possible. Right? And then I'm going to look back and say, well, how can we do better? And what are the different ways that we can approach this problem? So it had a lot of coverage, over press coverage. Why? Because this was a bulletproof evidence, it was all Americans, it was a large study, published in New England Journal of Medicine. There is a video by Cory Booker that brags about the study. So every time I have a day where I feel depressed, I just rewatch the movie. Well, I'll show you if you want. Anyway, it's you know, it had coverage, but with celebrity there comes problems, right? Because we had the biggest study, we're also getting a lot of scrutiny, a lot of criticism, because everyone who doesn't want to have the National Ambient Quality Standard revised, it's tried to attack, right? Our study in general, the other study as well. So what we have learned about, you know, this case study, right? So I think in the context of climate change related exposure and health, and knowing I've been working on this field a lot, it seems to me that there are at least 3 major data science challenges that are unresolved. And then we as a community, we need to work together to make the largest possible impact. And so I'm gonna go through that, and then, you know, again, at the higher level, but then I'm happy to take some Q&A. So first of all, and these are both real data science challenges, but also these are the data science challenges that the current industry is gonna try to pick to attack the current evidence, so then they can say the current evidence about harmful effect of pollutants, it's not credible, and so we shouldn't make the standards more stricter. So the first one is uncertainty quantification and propagation. And so this is important because I think that this entire area of machine learning, it's wonderful in terms of providing good prediction, but there is really still, and you know, I'm putting my statistician hat, really not good inferential base to quantify the uncertainty associated with this prediction from machine learning. From a statistician point of view, uncertainty is everything, right? And not only quantify the uncertainty, but then because in this context, we are estimating exposure to pollution. So I need to have a good estimates of how uncertainty I am, how uncertain I am, considering that my uncertainty might vary in different areas, because for example, in New York, I might be able to estimate the exposure pollution very well because it's heavily monitored, but in Kansas, not, right? So the level of uncertainty might vary spatially. But also then when I have this model, when I'm trying to estimate, and I'm start using the word causality, when I'm start using the causal effect of pollution on health or wildfires on health, how I'm propagating the uncertainty. So, you know, that's another quote, is that although our intellect always longs for clarity and certainty, our nature often finds uncertainty fascinating. And to me, uncertainty from a scientific viewpoint is fascinating. Unfortunately, from a regulatory viewpoint, it can be a threat if not considered carefully. And by the way, the entire, you know, I think, this is my personal view, but one of the biggest problem with the fact that climate change scientists have been criticized is because scientists tend to pay a lot of attention on uncertainty. I mean, keep talking about uncertainty, where I think right now there probably should be less uncertainty in the messaging. But I want to give you an example, right? So let's say that I am in Boston and I want to estimate the exposure to fine particulate matter in Boston. And these are 3 different models I can use. These are the same input, but 3 different output. They're using 3 different prediction models. One is a narrow network. The second one is a generalized mixed effect model. And the third is, I think it's called generalized weighted regression, right? So a different model give you a different estimates, right? I'm sure you know that's pretty standard. But this is what's nice about it. And Marianti, and her last name is so long it's impronounceable, so we call her Marianti. She's the universal Marianti. She's a faculty member at Columbia. She was at Harvard before, but she's leading this amazing project where she's building this ensemble learning. This is the results of an ensemble learning for estimating levels of pollution in Boston, but also there is that map on the right that this is one of the first attempts to do that, where there is the uncertainty associated with that prediction, right? And you see that when you get closer to Boston, the uncertainty is lower because there are more data and more monitors, but then when you're getting far away, the uncertainty gets to be larger. There is another element, and I'm not even bother you with all of that notation, but the other big element of uncertainty when you're doing health impact of climate change related exposure is a spatial resolution, right? So you have satellite data are available at 1 kilometer to 1 kilometer grid. Weather data is available at the monitoring station. Health data is available at zip code. Zip code and postal code change over time. All of this stuff about geographic information system and GIS, they're extremely important. And every single decision you're gonna make is gonna have impact in analysis, right? So these are the grid cells, and these are the boundary of the zip codes, and some data are available on one level, some data are available on another level. So there are so many decisions about how you realign the data in terms of spatial misalignment, but the importance is also how you quantify the uncertainty you're making in this decision and propagating the uncertainty. Again, when we're talking about informed regulatory policy, the most expensive federal regulation, where this study is going to be attacked, all of this needs to be documented and taught. Now, the other important things I want to talk about is causality. This is really important. And so how we assess causality of climate change and air pollution-related exposure on health, considering that in the context of climate change and air pollution, we cannot do a randomized study, right? So the gold standard of assessing causality is basically they take a group of patients, 20, they're randomized to be giving an orange pill. The other 20, they're giving them a yellow pill, and then they compare the outcome. right? Why randomization it's critical? Well, randomization is critical because you are eliminating confounding. By randomizing who's get the yellow pill and the orange pill, the two groups of people will be the same. On average, will have the same distribution of age, gender, poverty, and so on, right? Well, we can't do that on climate change. I mean, we can't randomize, you just go California and breathe pollution air from wildfire, you just stay here, right? It's not gonna work, right? So anything about environment has to be based on observational data. So as soon as you can only rely on observational data, you're never gonna have a perfect world of randomization. So you're gonna have confounding. Okay, so that means that in order to, now the other attack that has been coming with the Clean Air Act Advisory Board is that we cannot inform climate change regulatory policy, we cannot inform air pollution policy unless we prove causality from observational data. Now, we can never prove, I mean, this is a political attack, right? But still, that's prompt us to say, well, can we use the wealth of causal inference method to get closer to make a statement about causality from observational data? So I think also this is in general true in data science, right? So before data scientists, what we will do as a statistician is that you formulate an hypothesis, okay? Vanilla ice cream will make you more fat than chocolate ice cream. And then you randomize 100 people to eat chocolate and to eat vanilla, and then you will assess their body mass index. That's not what we do anymore in data science. In data science, first we're bombarded with data, right? We are flooded with data. So we're never gonna have a perfect control group, right? So that's why what the great and bad thing about data science is the great thing is that we have a ton of data. The bad thing is that we are never gonna have a perfect control experiment, right? So that's what I mean from hypothesis first to data first, from randomization to observation. And then, this is just a little bit of joke, but it's true, is there, in this new world that we live in, there is nothing we can control, right? I mean, this idea you can make inference and control, especially in the context of environmental exposure, doesn't work. And I think there is a nice analogy between them, but whatever. So just to give you an example of another attack of science in air pollution epidemiology, this was a piece in Science I wrote a few months ago. And basically, so this gentleman, Larry Cox, you can Google him. He has absolutely no scientific credential, but he's now been appointed as the chair of the Clean Air Act Advisory Board, which is the highest board that will tell whether the EPA and administration, whether or not we have enough science to lower the regulatory standard for fine particulate matter. And Larry Cox claims that the only way that we can do that is only if observational data can show causality. If observational data cannot prove causality that climate change related exposure kill, then we cannot assess, we cannot change regulatory standards. So in this piece, if you're interested, we explain the pros and cons of that viewpoint, which again, it's trying to set a higher bar of scientific credibility so then they can act, right? And that's, I think, is the strategy. But I think what's important though is that whenever you're trying, for any data science project you're trying to do, if you want to assess causality, if you want to assess the causal effect of income on outcome, or air pollution on an outcome, or wildfires on an outcome, there are a lot of advanced data science tools that allow you to, I'll never say prove causality, because you only can do that randomization, but get closer to causality. So for example, the most important thing is the design, right? You can take all of your data and you can design, do a design of your experiment in terms that you can approach causality. And actually, let me give you just an example. So here is the example. So in the context of environmental exposure, right? So let's say that you have two groups of the population. One is in Portage, Wisconsin, and one is Steubenville, Ohio. Portage, Wisconsin has a very low level of fine particulate matter, and Steubenville, Ohio has a high level of fine particulate matter. And you want to estimate the causal effect of going from low to high on the same mortality, right? One of the greatest idea, which is absolutely not mine, it comes from many, many colleagues in statistics and causal inference, is it's called matched analysis, right? And so this is basically the idea. Then there are, you know, enormous amount of sophistication. And so what you do, you take Jane. Jane is an high school teacher that lives in Steubenville, Ohio, and breathes high pollution level. And Jane will have a given health outcome. And then you're going to compare what the outcome of all of the people as similar as possible as Jane would have been if they would live in a low pollution area, right? So that we call it the counterfactual. And so there are some very basic fundamental idea of how, if you have a massive and messy amount of observational data, you can do matched analysis, propensity score analysis, I mean, you know, inverse proportional weighting, marginal structure. There are so many, but the idea is that you take a person that breathes high pollution level and has a given outcome, and you're trying to figure out what the outcome of the same person would have been if that person would have not been exposed to that level. And how you do that is finding among your massive amount of data an adequate control group. You were gonna find all of the ladies, they're similar as possible to Jane, same body mass index, same race, same socioeconomic status, same number of kids. The more data you have, same number of searches on Facebook, same bias things you buy on Amazon, but she lives in a clean area, right? And the greatest thing about data science is because we have so much data, we can get our twin sister or twin brothers around, right? So much easier than before, right? So that's really the idea. And then finally, just to conclude in terms of what machine learning can do and data science can do, this is a work led by a postdoctoral fellow in my team. So I mentioned to you the different subgroups differences, the fact that Black have a much larger risk than female or than white. So machine learning are a fantastic way to discover de novo subgroup of the population that experience health effect much higher or lower than the average population. So what we did in this analysis, and there are all the references, the code is available, is basically in the context of air pollution health effect, and now we're doing the context of wildfires, we basically first eliminate any type of confounding bias by finding these matches. And then we apply machine learning algorithm to identify subpopulation that experience higher effect or lower effect. So in this context, for example, the very elderly, the people that are more than 8 years old, and then also oh yes, and then they're also medically eligible. I mean, this was a simple example, but older they are, and if they're also eligible for Medicaid, clearly they're going to have much higher risk than the rest of the population. This is going to be very helpful in the context of wildfires, because I think it's really important to identify people with what type of precondition and disease and geographical area and age, race, and socioeconomic status are going to be the one that are most likely to be affected, not only by mortality, but neurocognitive outcome to wildfires. And machine learning algorithms are great to identify treatment, like we call it, treatment effect heterogeneity of causal effect across groups. I'm gonna and so finally, reproducibility and transparency. And this is really a response to the headline to New York Times today. So it was a kind of a crazy day. So today, if you open the New York Times, it's front page. Basically, there is a new rule that said they're going to try to pass and say that any epidemiological study that use data that's not publicly available cannot inform regulatory policy. And so this is a catch-22, because to change climate change rule and air pollution rule, what they need to do, they need to look at the number of lives that are affected by this environmental exposure. The great majority of the epidemiological study, when they look at health outcome, they have to rely on confidentiality patient data. This study, our study, is the only one that is not affected by this rule because we use government data. But still, we are not supporting the rule because that will discredit all of the evidence. But for us, I think it's really important. We are working really hard to really be as open science as possible, and having all of the data available, all of the code available, the entire workflow. Because also, I think it's important as this, when I show you the Marilyn Monroe quote and the research platform, I think it's important that I call it the living research laboratory that gets continually grow and updated, and so has to be based on an open science. Anyway, these are some of the photos of people in the team, and there are many, many more, many student and postdoctoral fellows that are working on this project, many more to come. And then I want to conclude and just spend a few more minutes on the data science initiative and Harvard Data Science Review. So Harvard has a university-wide data science initiative. There are two faculty directors. One is myself, and the other one is David Parks, who is a professor of computer science. We are university-wide, and I think we take a big pride of that because we believe that data science, and we call it the new science of data, doesn't belong to any specific discipline. It's everywhere. And so we are working on, we have so many initiatives, so please sign up for our newsletter and go look at the website, come to our events. We just had the conference. I mean, there is so much going on. We are thinking about these research teams as basically project in data science that will cut across all schools. So they range from the digital economy and the Internet of Things to evidence-based policies, which what I've been talking today, personalized health, data science, scientific discovery. So when you try to discover the novel new galaxy, new drugs, new material, so a very broad project. So a lot of things going on. We also have a corporate membership program. If you are working on a company, on an industry, we are still recruiting, not for very long, industry that will partner with the data science initiative to work together on research projects. We now have Bayer, Amazon, McKinsey, McKinsey Quantum Black, which are also here, Elsevier, and Harmony Analytic, which is a financial company. We're trying to get data science companies that are working on different sectors, so pharma, consulting, research publishing, because it's also important, and I'm sure many of you probably work in industry, that we work together, because data science often develops and evolves at a faster pace in industry than in academia, that everything is so slow. Finally, there is the Harvard Data Science Review. This is a open source, just launched journal. Zhao Meng, which is professor of statistics and former dean of the graduate school at Harvard, is the editor-in-chief. I think the title that Zhao Li came with is actually perfect, because it said a microscopic, telescopic, and kaleidoscopic view of data science. The goal of the journal is really to reach out to everybody. And if you see the first two issues, there are all different types of articles. There are still, the couple of rigorous scientific articles. There was an article from Michael Jordan, Artificial Intelligence, but there are also overview articles, perspective articles, what is about being data scientists. So, and the editorial board is purposely chosen to cover, a lot of sectors. It's free, and we also partner with MIT, and it's published by MIT. So I want to just conclude to just tell you things I learned, and I'm learning every day. I consider now myself a data scientist. I think I really, it's important to work on important problems. I think that actually being a data scientist or a statistician was probably not the sexiest job, and now it is. And I think having knowledge and understanding of these tools is actually give you tremendous amount of power. And I think this is a really an opportunity to work on things that are important, that could have a good value for a good societal value. Aim high, use your talent for the social good. And again, now remember that you can, because there is data. Data is not everything, but it's a lot. Remember the Merlin quote, data and shoes. Never compromise integrity and rigor. Again, with all data, also there is the sense of pushing things out quickly. You have a big data, you put an algorithm. I think that's important. Embrace diversity of across all spectrum. I think here we're all share this vision. Empower your mentee. They learn by examples, and you can never do it alone. And so I'm just gonna conclude with my puppy picture. So yes, she's now a 14 months old Labrador. It's a special advisor to the Harvard Data Science Initiative, and sometimes she consults to MIT for very high fee. Thank you. Any question, comments? Yes.
I was curious with the data sources you use with like Medicare and Medicaid data, which outcome metrics were you looking at? Did you target specific like respiratory conditions?
So the great question. So the Medicare files there are Part A, Part B, Part C, Part D. So Part A as hospitalization and mortality. Everything I showed in terms of the results were all done for all-cause mortality. However, we have all of the data for every single hospitalization by ICD-9 code. So there are a ton of studies and ton of things that can be done by looking at, which we did, by looking at respiratory admission, cardiovascular admission, neurocognitive admission. So all the ICD-9 codes are there. Data that we don't have, but everyone can gather, is the Part D data, which is doctor visit. Part B, sorry. Part B is doctor visit, and then there is also Part D, which are prescription drugs. So the research data platform I have is mortality and all-cause mortality and cause-specific hospitalization. But it can be augmented with these other files. Yes?
Thank you for this great overview. And you want to do also like prediction models that go like years into the future, like for, I don't know, from now?
Yeah, this is, so yes, we are doing that. This is not, this is not my personal area of expertise. Josh Schwartz, my collaborator, it's working on that also with Loretta Mickley, which she works on the School of Engineering Applied Sciences. But what we have done, we are published, and we're going to publish studies where we look at different climate change scenario from the climate change. So for example, in the context of wildfires, what we have done is we have looked at different climate change scenarios, and from the climate change scenarios, we have predict what's going to be the occurrence and the intensity of wildfires in the future, and which of the counties in the United States will be most affected. So there is work that is there now. The one challenge, so most of my work has been trying to quantify the public health impact, because I'm trying to provide the evidence for regulatory standard. So when you're doing the prediction, which is also the climate change science, I think that one of the challenges is that when you're doing prediction, then you need to extrapolate the public health impact, and people don't believe to that level of extrapolation, which is the reason why I'm focusing on this. But yes, we do that, and that's, you know, we have done, for example, so with power plants. So if you have all of the power plants, or if we phase down all the coal-fired plants, how much reduction in pollution we're going to have. But that's the beauty of now machine learning and this data, right? Everyone can do it. You can do it. The data are available. It's a question of hypothesis of running the machine. Yeah. Yeah.
So you looked at the United States, and I think the United States has a lot of good data for have you thought about other countries? Like, for example, India has very high levels of pollution, and there is like a lot of missing data, I would presume. So have you thought about how machine learning can help?
Yeah, no, that's a great question. So I think that also goes back to the importance of open science and making the code available. So yes, we have a partnership with the Public Health Foundation of India and with the Minister of India, and I call it capacity building. So we're actually going there and teaching workshop of how to use the science tool for health impact of air pollution. Because the greatest thing is about India is actually also, yes, they have less monitors, but the satellite data is everywhere. And so they have satellite data as well. So clearly the data sources are not as, you know, coordinated, and well, like they're here very uncoordinated as well, but they're not as advanced as here. But I do think that the goal is to take the model, and that's why it goes back to the research data platform. Because if you get the critical stakeholder, the government agency, the Minister of Health, to build the digital platform, then everything else is easy, because then people can analyze the data and make decisions. It's the building of the digital platform. So there is a lot that we are doing in terms of exporting this level of thinking and technology over there, especially in India and in China too. Yeah. Yes, and then I'll go there.
Thank you so much. This is amazing. And you talked about the resistance of regulators and the challenges that they've attacked you with. Have you received feedback from the medical community? What's their perspective on this study?
Oh, the community is super supportive. I mean, this study was one of the few studies ever where there is an editorial from the editor-in-chief of the New England Journal of Medicine. That's never happened before, that editor-in-chief of New England Emergency, right, the editorial. So no, the scientific community, but not only about my study, about all of the epidemiological study about climate change related exposure and health, is all in the same page. So it's the government and the current EPA administration, the current administration that is not. Yeah. There's a question.
Thanks for your talk. You were speaking when you come to resolution on the county level. I was wondering how you deal with scalability, like getting more precise and more coarse, especially when it comes to extreme events.
Yeah, no, that's a challenge. So we can get the both, for example, for exposure to PM 2.5 or exposure to wildfires related PM 2.5 or exposure to heat waves, we can get a resolution to 1 kilometer to 1 kilometer grid. Now the health outcome are available at the zip code. That's the smaller spatial resolution that we can get. So there is this challenge of aggregating up from grids. I mean, there is a challenge of spatial misalignment and then aggregating up. So there are different algorithms that we're using. No one can, so the best thing we can do is we do algorithm in a way that anyone will fully understand what we've done. And then we assess the sensitivity of our decision of aggregating up to the health impact. But with claims data, we're never gonna get to, for confidentiality reason, never lower than a zip code. But the zip code is much, much better than a county, that's what we used to have. Yeah.
I was wondering, how much does it cost to install a new air monitoring station? And is there any plan to use that geographical uncertainty model to figure out where you should collect more data from?
That's a great question. So some of our, so the question how much it costs, I don't know, but I know it doesn't cost much. I know there are colleagues of mine and not myself that in teams, they are doing exactly that. They're actually writing research proposal where the goal is to get funding to put additional monitors in areas that are not adequately monitored, so then they can get better exposure. Now, the degree to which better monitoring will improve the ability of the machine learning, that's still to be seen. But I think it's a very exciting area of research. Yeah. Any other question? Yes. Sure.
I was wondering if there's been any discussion about like a standard of reasonable doubt for proving causation, because it seems to me that it can never be like proved. Like if you get enough evidence, then that should be close to proving.
Well, yes. I think that, so you have to consider that there are two buckets of individuals. The reasonable and the unreasonable. So within reasonable, yes, of course. I mean, causality also can be viewed in so many ways. I mean, there have been, if you look at the literature, there are probably 5,000 studies on air pollution and mortality that shows air pollution is bad for you, right? So yes, I mean, and then I can show you algorithm, and I can show you that we have achieved covariate balance and all of the metrics, right? But you have to think that and again, this is probably a political discussion, but where we are right now, it's really raising the bar at the level that can never be achieved. So then no action can be taken. So that's, unfortunately, I feel that that's where we are, but still you have to keep the fight. So I do think the methods for causal inference are really valuable in observational study, because it is true that the observational study can be, like, for example, a lot of the studies on nutritional epidemiology, right? How many times you read in the paper, meat is bad for you, meat is good for you, eggs are, because there is a lot of confounding that's going on. So yes, but I do think that we are now, if you read my commentary on Science that talks about the feedback from Larry Cox, the Clinical Act Advisory Board chair, about the evidence of causality that needs to be achieved, it makes absolutely no sense. So.
And you mentioned about there are a lot of different data sources that are used like weather data, and there are some of the missing values in those groups. And how would you treat those missing values, or what kind of installation methods that you would use for those groups that has no data?
Well, the health data is complete. The health data is absolutely complete. The pollution data is complete. And the weather data is complete. So, of course, there are errors, but the number of missing data is very, very, very small. So that means that we either drop it, or whatever we do to interpolate doesn't, and then we use the census data. So fortunately, the data are mostly complete. There are no missing data. Now, there is uncertainty in the exposure, right? So there are very few missing data in these data sources. Yeah.
One of your slides, you had pictures showing a few different models.
Yes.
And how the results were a little bit different. How do you, I guess, how do you decide which one to go with? Is that more exploratory?
Well, so what we are doing, we now have a 4 years research project that does ensemble learning. So not specifically for these three models, but basically we fit different models, and then we take a weighted average of the different models, and they're weighted based on their different measures of accuracy of the way that, you know, they are being performing. So it would be, so that's why we call it ensemble learning. We take multiple models, feed to the data using different hypotheses, and then we take a weighted average that is weighted by their ability to predict well. But there is a lot of research, because when you are weighting across models, the weights need to vary spatially, because some models have a good predicting performance in, you know, in some area and less in area. But that's what I mean about, in terms of really data science methodology, this is, I think, a very interesting area of research. And by the way, I'm showing pollution, about wildfires, droughts, heat waves, cold waves is exactly the same statistical problems. I mean, everything I said apply to every climate change related exposure, not only to pollution. Last question.
So one thing I was thinking as you're talking that might be kind of frustrating is that people can move from zip code to zip code.
Yes.
Did you ever explore or have any idea someone moved from a high-risk area to a low-risk area, how that might affect their outcomes, or if somebody's exposed for slightly longer than another person, how that might affect them?
Yeah, no, that's a great question. So there is a PhD thesis that's been written right now exactly about that. This is why, you know, with the data, you can conquer the world. So yes, so we have a PhD student, and she's actually that's a perfect experiment. You know, you're exactly right, because it's very interesting to look at the movers and the non-movers. So, so I don't know the answer to that, but there is work that is being done to actually, I mean, the Medicare data tracks between every 6 months, a year when they move, because, you know, they need to know based on where they go and see the doctor. So we have a little bit of, it's not perfect, but we have information about that. So, so that has been done. Not many people, I mean, I think it's 14% of the population moves at any point during their entire time they're in the cohort. So I mean, there's a big number, but I would have expected would be more. But yes, this analysis is being conducted, yeah. Okay. Thank you for coming. I really appreciate your attention and the excellent questions. So thank you.
Thank you, Dr. Dominici. And Lisa from DigitalOcean is going to talk about what's happening next and also talk about DigitalOcean for a second.